started? Hello, everyone. Hello? Hello, everyone. Thank you. If I could have your attention, please. I think we're about to begin. I lost one of my panelists, but here we go. So thank you, everyone, for joining us today. I'm Joe Helble. I'm the Dean of the Thayer School of Engineering, and I'm pleased to have you join us today, as well as many of our alumni and friends who are live streaming in for this afternoon's discussion. Today, we celebrate the upcoming presentation of the Bernard M. Gordon Prize for Innovation in Engineering and Technology Education being given to Dartmouth's Thayer School of Engineering, a prize that may well be the largest and most significant award for education in the country. In celebrating this, we'd like to do something a little bit different today with our weekly seminar. Instead of a research presentation, we're going to have a conversation with Thayer School of Engineering colleagues, in part on experiential learning, but more broadly on ways to foster creativity in engineering education, on innovations in engineering education. Our participants in this panel discussion this afternoon are four distinguished educators from the Thayer School of Engineering faculty. Introducing them from my immediate left, Professor John Collier, the holder of the Myron Tribus Professorship in Innovation, one of our Gordon Prize recipients, and the person perhaps most closely associated with what has become, at Dartmouth, an iconic course in engineering and engineering design taken by majors and non-majors alike, and known to all here at Dartmouth simply as Engines 21. John has been a member of the Dartmouth Engineering faculty since 1979, and he is the Carnegie Foundation for the Advancement of Teaching New Hampshire Professor of the Year for the year 2010. At John's immediate left is Assistant Professor Solomon Diamond, a mechanical engineer with research interests in neuroimaging and teacher of courses in computer-aided design, neuroengineering, and solid mechanics. Sol is a consummate tinkerer, someone whose courses and projects are never the same year to year. Sol has been a member of the Dartmouth Engineering faculty since 2007. At Sol's left is Professor Vicki May, an associate professor of engineering, developer of project-based courses in architecture and structural engineering, co-PI of a major NSF grant that pairs STEM graduate students, engineering and science graduate students, with middle school teachers, and the creator of Design It, Build It, a summer engineering design and project-based experience for high school students. Vicki was the recipient of both the Thayer School of Engineering and the Dartmouth College Outstanding Teacher of the Year awards in the same year in 2012. This is the only time that has ever happened. And Vicki is the current Carnegie Foundation for the Advancement of Teaching New Hampshire Professor of the Year. Vicki has been teaching at Thayer School since 2006. And finally, at my far left is Professor Tilman Gerngross, a professor of engineering, serial biotechnology entrepreneur who has founded or co-founded 5 companies, 4 of them in the past 7 years alone, and including 2 Upper Valley success stories, Glycify and Atomab. Tilman is presently the Associate Provost of Entrepreneurship and Technology Transfer at Dartmouth, and he's been a member of the Thayer faculty since 1998. So our format for today's discussion Thank you. Our format for today's discussion is that I will start things by asking a question of each panelist to give them a chance to talk about their philosophy and approach and some of the more creative aspects of their educational work in one specific instance each. I'll then moderate a discussion among them with a range of questions we'd like to discuss about education and the state of engineering education, and then for the last portion of our hour, I'll open it to general question and conversation with the audience. Now, as we stand here today in 2014, many observers today and frankly over the past decade have been commenting that they feel that engineering education is at a crossroads. The National Research Council has released reports calling for dramatic change in engineering education with incorporation of more project-based learning or more broadly experiential learning that goes well beyond. The explosive growth of organizations like Engineers Without Borders, or here at Dartmouth, our humanitarian engineering group, make it clear that students themselves are seeking to enhance their education through real projects that affect real communities in the real world. Some have also suggested that perhaps part of the reason the gender disparity remains so large in engineering nationally is that many programs have been slow or perhaps even unwilling to experiment to bring challenging projects to students and use them as a basis for part of their education. At the same time, in a world where massively open online courses, or MOOCs, have gone from a curiosity to what some are hailing as the means to reduce the cost of higher education in just a few years, there's a drive to use technology to make education of higher quality, less costly, or both. Each of our panelists has addressed some of these challenges in very different ways, creatively in the classroom and in project work. And so I'd like to start the discussion by asking each of them a question to describe something that they have done that engages their students and encourages creativity. So John, since you're seated closest to me, I'm going to start with you. So John, as I said at the outset, you're the faculty member perhaps most closely associated with the introductory required projects-based course that's taken by all majors in their first or second years, and also by a very large number of non-majors. Could you take a few minutes to describe Engines 21, both the course and your approach, which you've characterized, at least in our conversations, as something of a guided apprenticeship?
Sure. I contrast a guided apprenticeship with straightforward experiential learning. And experiential learning is when you climb the tree and the branch breaks and you land on your head on the ground, you've learned something. That was experiential learning. If it were guided, a parent might come out and sit with you and talk to you about what just went on. And is that branch dead or alive? Is the branch small in diameter or large in diameter? Were you in a willow tree or an oak tree? And how far out on that branch were you? And what kind of stress were you applying? And so that would be a guided apprenticeship. So in Engines 21, what we try to do is encourage the students to pick open-ended projects, something that would be of interest both to them and some clients, some users, and then attack it, but you guide them the whole way. And it's a very labor-intensive business. I don't do it single-handedly. I typically have a class of 60 to 80, and we'll have somewhere between 15 and 18 TAs, one TA per group to guide them. We have 4 folks in the shop who are trained to take care of these students and guide them. And then we have some electrical engineering folks and computer folks. So there's a network of folks that make a net under the students to help guide them. If I take an example of a group that did a project this winter, the project area, general area we had was solving, improving the quality of life in winter. And one group decided when they went out and started meeting with people in the community, and that's one of the key characteristics, get them out of the classroom, get them out into the community. They talked to people in the community, and folks had solar panels but were frustrated to get snow on it that was difficult to get off. They were thinking of different ways of dealing with it and worried about falling off the roof and injuring themselves. So the students sat down, started brainstorming this, thought about brushes and warm water and coatings on the panels or pieces that they could cover the panels with when it snowed. They finally sat down and realized what they really needed to know is what the customer wanted. So they went back out, talked to the customer, asked them what their specifications were. And it turned out the customer is very interested in aesthetics, what this thing looks like. They don't want to have to use power off the line. They want it simple and straightforward. Short story out of a long story, the students came up with a bunch of techniques which they applied, and they failed. They tried warm water, and it didn't work. They tried brushes, and they didn't work. And one of the things I learned as I started not only teaching this course, but in the early days when I took it, you have to fail. And what Fred Hooven, my mentor, used to say is fail early and often. And because you learn from every failure. You don't learn if you're not failing, and you're not learning if you're not guided in trying to understand those failures. So anyway, the students eventually came up with a solution that was to heat the panel. But they tried heating it from the front side, and the downside of that was that they had to use the panel itself as the heating element. The users said, does that work? Yeah, it works beautifully, but it may lower the life of the panel. They didn't like that. Came up with a way of heating it from behind, easily retrofit. people really liked it, but then they had to do the immersion process, which is, does it work? And so they go out and put snow on the panel and set it up and sit there at night waiting for the panel to heat up and the snow to fall off. And eventually it does, and they're all excited about that. But it's an immersion process and a guided effort and not straight experiential learning.
So John, if I can, before I move on to the next question, could I just ask you to just comment on the process a little bit? Because when I arrived, one of the things that fascinated me the first time I sat in on some of the project presentations is what you and the other instructors who teach this course are able to do in just 10 weeks, where you take a group of students, freshmen or sophomores, who have oftentimes done very little like this at this creative, and they go from knowing nothing to identifying a problem, brainstorming possible solutions, all the way up to building, designing, testing, doing an economic and patent analysis. So just tell our audience a little bit about the structure and the process.
Structure starts where you divide the students into typically a group of 4 or 5. The students then go out and work in the community to find out a project that will fit into their general area. Again, it might be something like recreation. They talk to people who have problems in recreation or in trying to help the elderly or help the handicapped, and come up with something that appeals to them. One group looked at a handicapped girl who really wanted to be able to play music, but she couldn't communicate that. She had a head stick and couldn't hardly communicate what her problem was. And when the students asked, she said she wanted to play chords, and they didn't really know what that meant. Well, it turned out she had one of these little Linus-type pianos, and she couldn't bring both hands in to run it. So it's learning. That the first part of it then is learning about what the problem is and how you get to deal with the person or people with the problems. Then you get their specifications. What do they need for a satisfactory solution? Then they come back in and they present to a board. So we have a review board of 5 or 6 folks. Here's what we think the problem is. Here's the background. Here's the state of the art. Here's what's been done in the patent world on this issue. And here's what we propose to do. And they get feedback from the board for an oral presentation. They do a written piece. You feed that back. And then they go and begin to work on this in their team, typically in Couch Lab. How do we go about tackling this problem? And most of them end up wanting to build and needing to build something. And for that, we actually train them week after week with sessions in the Thayer School Machine Shop, with other sessions in the electronics lab. And so one of the things that we've been careful to do is make sure that 100% of the kids that come through 21 learn how to run equipment. They've all been trained individually in the machine shop, all been trained how to use computers, how to use computer-aided design software, how to run the mechanical equipment. So they're all set up so that they can build these things. Begin building really rough prototypes. They go out and test the prototypes, show them to the users, get feedback again. Some of the fun ones are groups that do things like sleds, where you've designed a sled that you think is better than what's out there and more controllable. You get the faculty to loan you their kids, and they go out and try this out. You get some very interesting feedback, especially when you lose kids because they bounce off and stuff. So, but that's all, how do you fail early and often so you can learn how to do it better? So the punchline then is they come in, do a second presentation, here's our progress, they do a third progress presentation, and in the end they do a final presentation. And one of the keys is at that time that you look at this device that you've built and the feedback you got from your customer, and you put together a business plan. How many people might be interested in buying one of these? What does it cost to produce? And can you actually make a business where you could do this?
Thanks, John. And what's great about it, too, is it takes students in many ways back to the roots of engineering. Everyone, despite their experience coming in, is actually designing and building, machining something before they finish the course. So, Vicki, you're teaching a range of courses right now, but one of the ones I find fascinating is your effort in structural analysis, structural and design, and where you take a slightly different approach in which the entire class designs and builds one or two structures, and they're doing them for a specific customer, for a local school, a community center, a nonprofit, or a recreation area. Tell us a little bit about your approach, your reasons for taking it, and some of the challenges you find in organizing and running a class this way.
Okay, so it's the class I'm teaching this term. I started doing projects because structural analysis, students can get the analysis. I mean, it may take a little while, but they'll figure out how to do the analysis. But they don't really know how to apply it to the real world. So they can do textbook problems, but they always have questions like, a pin connection versus a fixed connection, and how do I model it, and how do I make those decisions. So I wanted to get them out and do something real as opposed to textbook problems. I started by having them just design something, and that takes it one step further, but I decided they really just need to build something. They need to be immersed in this and figure out how to do it on their own. It's generated so many questions and so much, they were so invested in the projects. So the projects have been different every year. The treehouse is probably what made me the most famous. And I'll never do a treehouse again, but we have one treehouse. Sorry, Joe, if you wanted more tree, no. So another approach that I like is we do a lot of competitive, and a lot of their problem sets are individual. So I try to get them a structure and do something cooperative. And I'm big on the cooperative learning model. It's from Minnesota, where I'm from, so I have to promote that. So everyone has to contribute to the one project that is going to get built, one or two. If I get a bigger class, I need a couple projects to make that work. Grading too. Part of the reason I do that is I hated group projects as a student, because I was always that anal student that did it whether anyone helped me or not, because I was going to do a good job. So the cooperative learning model forces me to think about individual accountability as well as group accountability. And I have a personal rule that no more than 50% can be a group grade, so that we can make sure everyone's working and doing their contribution. I really push them to try to be creative, especially in the first phase. So they presented their first phase for my current class a couple weeks ago. One of the more memorable was an underground jacuzzi, waterless. Okay, we're not building that, but they definitely pushed the envelope and had some neat ideas that we're taking forward. We're building structures for the family place just down the road. I like them to get in and talk to the community members, so we made a trip out to the family place. Every project we've done, we've spent a fair amount of time with the clients, so they hear from the clients, and they've gotten mixed messages this term on one of the people at the family place wants one thing and one wants another, and they have to reconcile that, but I think that's good for them. Let's see what other issues.
Who are some of your other clients besides the family
Haven.
place?
So we built some play structures for the Haven last year.
Which is?
The Haven is a nonprofit group in White River Junction, that works with the homeless. They have a lot of children that come play at their play and stay at the Haven. So they wanted some play structures out back for their smallest children. I've had students. So we did a nursery school early on. It was one of my first projects. My class was small, and I'd said, we're going to build something. And one of the students, a woman, came to my office and said, we really have to build it. The kids are counting us. And she was almost in tears. She said, are you sure we can get it done in 10 weeks? And I wasn't. But I said, yes, I'm sure we can. But the students take a lot of ownership for it, and it's amazing what they can get done in 10 weeks because they're invested in it. And the questions they come back with, for the treehouse, we got a truck stuck in the mud, then we got a tractor stuck in the mud, so we ended up carrying everything up, and then they're like, how are we going to get things in the tree? And I don't know, how are we going to get things in the tree? We got something in the tree and it didn't fit. Your son was one of them. Well, we're going to have to make it fit. We got to figure it out. So it's problem solving. It's looking at the connection, and they'll ask, how do I model this? And I'm like, well, try it a couple ways and see what fits best. So.
Right. Thank you.
Yep.
Thank you. So, Saul, as I said in my introductory remarks, you've already, in your brief time here, gotten a reputation as the consummate tinkerer. Tell us a little bit about the twist cars and the die wheel, what they are, how it works, why you think it engages the students, and why you change it so radically every year.
Okay. So this is part of a class that I'm teaching right now. It's computer-aided mechanical engineering design.
For what level students, Saul?
So this is generally for seniors and our fifth-year engineering students, usually a good mix of those two groups. Once in a while, a brave third-year student comes in. And it builds on other courses we teach here. So we have
Faculty take it every once in a while.
Faculty even take it once in a while. So it builds on solid mechanics. It builds on machine design. And so by the time I get them in this mechanical engineering design with CAD, they're ready to be challenged. These are students who are often looking towards careers in mechanical engineering and design, and I take the opportunity to move them outside of what they have seen in their daily lives, what they have thought about. I want to give them design challenges that will sort of put them in an alternative reality where they're able to unlock some creativity and really go a different direction. So I also happen to think that sometimes it's okay to have a lot of fun in an engineering class. So I was looking around for project ideas and was in a toy store at the time. And I was riding around whenever I'm in a toy store, I got to try out the fun thing. So there was this plasma car. You sit on it and you kind of wiggle the steering wheel and it moves you forward. And I thought, gee, that would be fun to make with engineering students. We could make big ones. We could make them fast. We could have races. So I brought this idea to the students, and they got on board with it. So we had twist cars, and we did this race a couple of times, and each year I'd run that, they would get faster and better, and I started to see ideas that I had never dreamed of getting integrated into these things that were making them smooth, fast, and really fun to ride.
So if I can interrupt, maybe this is urban legend, but what I've heard is not only did you bring the idea to the class, but you walked in with a stack of patents, slapped them down on the table, and said, here's the state of the art that covers this. Your job is to innovate beyond.
I did do that. Yes. So I.
Thank you. So that's verified, and I will note that in your file at the end of the afternoon.
So I wanted students to know that when you're working in design, you're not working in a vacuum. Almost any problem that I've dreamt of, where I think I wake up, that is just something no one else in the world could have possibly dreamt of that. And you go to the literature, you look in the patents, you look and see what's out there, and sure enough, someone has worked on that problem before. And I wanted students to find that out. And so I gave them I gave them about 10 patents for the twist cars to look at. And of course the plasma car included, but other ones as well. Some that had made it commercially, others that did not. And they had to come up with designs that were significantly improved beyond anything that was out there. I needed to see innovation in their design work that was not just new, but actually served a function, made these things faster, better, more comfortable, more maneuverable. It needed to show up in the performance. We did that for a few years. I thought now students have learned too much from prior years. It's time to mix it up. And so I looked around for other crazy vehicles, found some interesting websites talking about vehicles with not enough wheels, and came up with the idea that we should build die wheels. So this is when you have two giant hoops in a frame that you've built that rolls inside of the hoops. And these are pedal power, and it's more like tank steering. So either you've got levers or you've got some kind of cranks, or some way or another you've got to figure out how to propel and steer your frame inside these giant hoop wheels. And we raced them outside on the lawn outside there. So we did it last year. We had moderate success. Some worked very well. Other students had very innovative ideas, but were challenged by execution.
What exactly do you mean by that?
Well, it's to go from concept to race in about 4 weeks, where you're building a machine that is as big as you are, and it's going to carry your body and 3 other people on your team in a relay race. That is hard to do, and you've got to be completely on the ball, organized, creative, and decisive together, and execute it well using all the facilities that we have here at Thayer. Lots of support from the staff, of course, lots of support from other students sort of pulling together, lots of TA support, and we get it done. And that's part of it, is that you throw students into these challenges that are terrifying at the outset, and then on race day, it can be a brilliantly wonderful time just to see that energy come out and to see the creativity manifest in the physical world. And that's the kind of experience I think students need in design, to unlock that kind of energy and be able to then take it and channel it in other directions as they want to in their careers.
Right, thank you, Sal. So Tillman, you're famous locally, not just for being a successful biotechnology entrepreneur and for asking provocative questions, but for teaching courses in which all students are examined individually, adaptively, through oral exams tailored to the particular student's level of knowledge. Now, at a liberal arts institution like Dartmouth, that's certainly not an unfamiliar approach, but in a quantitative engineering course, it's essentially unheard of. So how does it work? Why did you go down that path, and what are you hoping to accomplish by doing it that way?
So there are 2 benefits that I've observed by going down that path. And the first one really relates to the students, that higher education in a way is no different than in other areas of human activity, where the outcome that we measure, the metrics we measure, and how we measure them has a big influence of how the system ultimately works and what output it produces. And the course in particular where I use this approach, Introduction to Biotechnology, is a course that is very rich in concepts. So it's perhaps less quantitative than some of our other engineering courses, but there are a lot of different concepts. And what our students typically have optimized around is an exchange of question and answer in a written format where it's very easy to give the appearance of knowing what the concept is while actually not understanding what's going on. And I found that frustrating because it ends up resulting in discussions after the exam. Well, if you read it this way, that's what I actually meant. And those types of discussions are not only unsatisfactory, but it's just an ongoing negotiation that I didn't want to be part of. So I felt two things. One is that if you actually have the students sitting in your office and you have a verbal exchange and you ask a question, you tell them exactly what the standards are in terms of what it means to answer the question correctly. The second you see them veering off in the wrong direction, you follow up, and so the amount of information you can exchange over a 20-minute period, in my opinion, is like a 2-hour exam or even more. And so it's very direct and very effective in that regard in terms of assessing knowledge. The other thing that I feel we overemphasize is assessing knowledge through written exams or papers. And when you look at actually what happens to our students once they leave this place is, yes, the first interaction is you send in your resume. The second interaction, provided you are applying for the types of jobs we want our students to apply to, is you meet an intelligent, knowledgeable person that you hopefully are intimidated by because you're aiming high, and you have to demonstrate to that person that you know something. And so at the beginning of the term, when I explained to them that there will be 2 oral exams, most of the students have not had oral exams before. It scares the living bejesus out of them. But once they have it and you actually look at the teaching assessments at the end of the term, the vast majority of them sort of say that's one of the best experiences that they've had, sitting in the office with the professor and being challenged through this verbal exchange. They find it very rewarding. And so as I tried it and noticed that the feedback was very positive, I kept on doing it. And the other sort of side effect or second element that I felt was very helpful is when I ask a particular question to 5 students over the course of these exams take a long time. It takes 2 days to sort of work through the whole class. But when I see consistent weakness in certain areas, I quickly realize that's my problem. Because if they all sort of don't understand particular aspects or particular concepts, I must have done a pretty poor job in explaining them. So it's, again, a very direct feedback loop to the educator or to the lecturer of, you got to spend more time on this, so you have to explain it in a different way to get that particular concept across. So I found both of these to be meaningful benefits that I've seen both for the students and for the way you refine your approach to teaching.
Do you find that it works better with students at a certain level? You know, juniors better than BE students or master students, or do you think it works equally well across the board?
I think it works equally well across the board. Where I see the biggest gap is that the students that really understand the material, they love it because they're sitting there, you're asking them questions, and they're like, yeah,
it's a
I
chance to
studied
show
for a reason,
off.
right? Here's my professor, and I can shine with my knowledge. The students that are used to sort of just about scrape by, for them it's painful. It's like showing up at the dentist and you didn't floss and you didn't brush your teeth, and it just goes south from there quickly. And so the gap is much bigger between the star students and the ones that took the class probably for the wrong reasons. So.
All right. Thank you. So thank you all. So what I'd like to do now for the next 15 minutes or so is I've got a series of questions I'm going to throw out. I'll ask perhaps 1 or 2 of you, maybe 2 to answer each. I might one of them go to all 4 of you, but I'd rather keep it moving around. So this is like an adaptive oral exam. We'll push you just far enough. See, so let me start by asking a question of interdisciplinarity. So what does interdisciplinary in the context of engineering mean to you personally, and do you consider your teaching to be interdisciplinary? Why or why not? So Saul, I'm going to pick on you first. What do you think?
Interdisciplinary is absolutely central to what I do in my research life and in my teaching. So although I teach these courses in mechanical engineering, I also teach a class in neuroengineering. And you normally don't hear neuroengineering and mechanical engineering in this, together, but those are the two worlds that I live in every day.
So does it mean then bringing non-engineering concepts and engineering concepts, and is that what you mean by interdisciplinary in your context?
So it's two core areas of traditional learning, and there are synergies and there are there are insights that come from living in two different worlds, and I think it's a really important part of what we do here at Dartmouth in terms of liberal arts, in terms of blending liberal arts and engineering together, and so having faculty who are also engaged in very different ways of interacting with traditional disciplines brings that right to the front. And so I will end up sometimes bringing examples into a mechanics class that might seem a little odd to the students at first, but it's comfort zone for me. And so that also opens up the door for students to think, oh, well, maybe this other area that I've been learning about somewhere else on campus is relevant in some way, in some unexpected way, and that can lead to new insights, new discoveries. And it's a different kind of process from traditional problem solving. It's an emergent property of interdisciplinary study and learning.
I also understand, maybe I shouldn't ask this publicly, but there's another one of these stories that you once used dance to demonstrate. All right, so it is true.
Yeah, that's true.
All right, now you have to comment on it.
Sure. So this is part of, sometimes you're giving a traditional lecture and you feel like maybe people are falling asleep. And so if you were to get up on the table and do the moonwalk, it might wake people up. So I did that.
All right, I'm not going to push on that any further. I think let's move on. So, Vicki, what about you? What does interdisciplinary mean to you and for you?
He made me stand on a can once in class. We co-taught a class, so yeah, I've seen it all. Interdisciplinary in my class. I co-teach a class with an architect. I've co-taught a class with Professor Diamond as well. So that was definitely interdisciplinary, and we definitely tried to keep it not one person teach half the class and then the architect teach half the class. So we try to bring them in and meld them and show that we need to have integration between engineering and architecture. But in all my classes, just having the mindset that this is, yes, we're talking about structural design, but there's lots of things that feed into that. We need to understand materials. We need to understand what the client wants, so there's psychology going on there, and just all those important factors that come in. One of my groups this term is working on a snowflake project for the Hookset Welcome Center. It's a small group and it's kind of a special project, but there's actually not all that much structural in it, and they were talking today, but do we have to understand the glass properties? So I'm like, well, the project's not going to work if you don't. So getting out there and looking at different things.
So let me ask you each to think about a question. So the National Academy of Engineering several years ago identified 14 grand challenges, big problems that we expect to be facing society for a century in areas like healthcare, energy, sustainability, communications, security, that should, they argued, be problems that the engineering community, the folks that we're educating today, are coming up prepared to tackle. And so how do you think more needs to be done to make engineering education relevant to these grand challenges, to the big problems that our students are going to be facing when they graduate? So Tillman, what do you think?
I mean, one of the things that Vicki said earlier really resonated with me, and that is that we have very, very intelligent students here. And so when you look at sort of your traditional textbook, in theory, you could say at the beginning of the term, here's the textbook, work through the various chapters, I'll see you at the end of the term, and they will master the material to a point where they can solve all the problems in the problem sets. But that's not a very satisfactory experience for them or for us, for that matter. So I think at the end of the day, we're contextualizers. Our job is to take that knowledge that is in those textbooks and make them relevant to what's going on right now. And sorry, what was your question?
Exactly that. Big problems in healthcare, drug development,
the grand
challenges.
Sorry, yep. And part of that is explaining to our students what those grand challenges are. And of course, they have to pertain to the particular subject in some way, and why they're such big challenges. And I think it's again a very powerful tool of connecting the world they live in to a textbook, which inherently gives relevance, and people want to do things that are relevant. So.
I mean, it strikes me that the project-based approach that you've all described in different ways is immediately germane, relevant, and appropriate for trying to do this. You can pick a problem in a broad area. John, you described this in Engines 21 so well, where you're giving students, okay, I forgot what you said about this winter's theme, projects and processes to improve the quality of life in winter. That's not just, well, that's a grand challenge in Hanover, New Hampshire. It may not be nationally, but that's the idea, connecting them to outward-facing problems that are significant and going to impact their careers. So let me ask, John, let me ask you a question. Tillman and Vicki both touched on this a bit, talking about the creativity of the students, and I'm struck that many of us say students today are different in some ways than they were 20 or 30 years ago. Is that, so you're nodding your head, yes. What? Should I move on to the next question, or would you like to elaborate?
It sort of smacks you in the face, which is so interesting. And so what happened with me is about the year 2004, 5, 6, I came to the realization that as much as I enjoyed teaching 21 and having the kids work on projects, that there were two things that were going on. One was that within a group, you would have the people who did and the people who watched. And within the group, whoever fabricated and didn't do the written report or didn't do the patent search or the literature search, but actually built the thing, whoever was doing that had a set of tools that was different from what the other kids had, and not very good tools. And that this was different. So for the first bunch of years that I taught the course, most of the students who would come in were by nature tinkerers who said, gee, I've been building go-karts or tree houses or whatever, and I'm not very good at it, and I want to get better, so I'm going to be an engineer so I can make a faster go-kart or a better plane or whatever it is that they're interested in. And that they came in with skills. I mean, they had thumbs that were beat up from hitting them with hammers, and so you were sort of preaching to the choir, as they say. And more recently then, as of past the year 2000, the students who came in mostly seemed less into that kind of thing. So we had clickers that year, the first year of clickers, where you could anonymously answer a question, because questions that I was going to ask were a little intimidating. So I passed out the clickers, and I said, how many of you have ever drilled a hole of any kind in anything? And if you had done this in 1990, people had been throwing stuff at you and laughing at you. And about 50% of the students had ever drilled a hole in anything. Well, I mean, it seems a little unusual here. Unfortunately, I ended up in a meeting up campus with other faculty, and I ended up in one of those moments where I'm talking to the person next to me, and I said to Saul, I said, do you know, I asked my class, and only half of them had ever drilled a hole. Well, of course, the room was quiet at that instant, and everybody looks at me, and the person leading this meeting looks over at me, and she says, and why would you want to drill a hole? So anyway, things have changed, and so there we are with half the students don't know why you drill a hole, and certainly had never tried. And when you go to the next level, if you ever run a lathe or a milling machine or a welder, or no. And so I sat down with Kevin Barron who runs our machine shop, and said, we've really got to change this. We've got to do something really quite different than we've ever done before. And the way 21 had always been worked is it was open. So you had to come to class, and then the rest of the time was work on your project, and there was never a lab. So in 2007, we set up a lab. And you had to come for 2 hours a week, and we were going to teach every student, not only to drill holes, but to how to run milling machines and lathes and bandsaws and you name it. And so if you had a group of 5, you had a TA for each group, and the TAs then got trained by Kevin so they could help out, and Kevin has 3 other professionals in there as instructors. And so we took it on ourselves. We're going to take 60 to 80 kids, and we're going to teach them one at a time how to run all the equipment. And they did. And of course, when the course reviews come, I'm panicked because everybody's going to be upset because they blew 2 hours a week. And it turned out they loved it. And so ever since, we've been doing that and trying to get better. So everyone who takes 21 learns computer-aided design at one level or another. They all run all the equipment. And what we've done then is try to generate a mechanism to do that where the women are as well treated and interested and encouraged and supported as the guys were back before we ever had women interested in engineering. And so I think they found this to be a comfortable, supportive setting, and I think it's helped us to bring women into engineering and to get everybody, when they hit Saul's course, nobody's surprised that they're going to have to do more SolidWorks. Nobody's surprised they got to build stuff in the machine shop. And some of the students we send you are actually quite skilled before they get to you.
Yeah, I think that's, it's the gender gap issue, and that's one of the last questions I want to come back to in a minute and ask a few of you. But I've been struck by that it's a wonderful way of leveling the playing field, and so a certain group of students might perceive that everyone else has more experience in this area, and as soon as you're talking about something hands-on, it could be a barrier, but by having every student go through it, you immediately eliminate those concerns. And I think that's, the fact that our engineering enrollments at the undergraduate and graduate level run from 30 to 35% every year, which is twice national average. I think things like this are a huge contributor. So I'm just going to ask 2 more questions before we open it up broadly, and we'll be fairly focused here. Tillman, I wanted to ask you this question. So the Thayer School today is receiving an award for an approach to teaching engineering entrepreneurship that extends from the moment students set foot on campus all the way through to the PhD. I wanted to ask you, what does entrepreneurship mean to you in the context of your work? What elements do you see in your own particular teaching, project advising, research that help foster the skills, appreciation, understanding, enthusiasm, desire to our students to take their work and have an impact that goes well beyond just handing in a project at the end of the term?
Yeah, I think it weaves together several of the themes that we've already talked about. One is the big challenges. What are the problems we would like to work on and ultimately solve? And I think the academic profession is very much tied to ways of assessing metrics of success or impact that are very much driven by how many publications, how many people cite my work, and all that gets tallied up, and that means you are a better faculty member than if you have fewer citations. So we have our own system by which we try to assess the impact of our scholarly work. And most students don't care about that, quite frankly. What they do care about, though, is they do want to change the world and make it a better place, and they want to have impact. And so I think that's where these themes sort of come together, that as you identify meaningful problems that they would like to solve and sort of chart a path by which they can, in fact, contribute to that or do it themselves, it typically generates a lot of excitement and interest. And so it's a broader dialogue that I think we're trying to broaden beyond just engineering school, that the way we at Dartmouth should or are starting to think about impact has to go beyond traditional methods of assessment. But and I think Terry actually floated this concept of lives touched or some other metric that goes beyond what we typically do. And I think we're making really good progress in at least having that conversation, and you can absolutely see it amongst the students. It really resonates with them, and you see it in the PhD innovation program and other activities that we are promoting. But so I believe it's tying together the grand ideas, solving those, the grand problems, and working and solving some of them that gets our students excited, and seeing that in this place here, we value that and we celebrate it when there are successes. I think it's sort of gradually but steadily changing the culture.
Do you think it can be taught? And I ask this and answer this mindful of the fact that we're about to receive an award for doing just that. But do you think do you think entrepreneurship or the skills?
Signed, right?
I mean, there's been an argument that's existed for many years. Some prominent venture capitalists, no one on our board, but have said, I recognize an entrepreneur when I see one, you're born with it. And I don't buy that, but I'd like your thoughts.
I think our actions and our thoughts are informed by our own experiences. And I think there's a large role that we as faculty play as role models, and showing students that you can do something that has real impact, I think inspires them, and they will try things that they otherwise may not have tried. And so I think, as John is saying, the more things you try and then perhaps fail, the more you learn. But ultimately, I do think you can move the meter by encouraging more of our. I remember when I came here in 1998 and was talking to the people in career services, and the metrics at the time were we landed X number of students at Microsoft, we landed X number of students at Ford Motor Company, and I thought, that's interesting. When I last checked, Bill Gates was doing just fine. I want to find a way of finding the next Bill Gates, or at least encouraging people to think at that level. Right. And again, these things take time, but I think we are making progress.
Right. So last question, and I'll toss it up as a softball to Saul and Vicky, since the two newest members of our faculty on the panel. How can we reduce the gender gap in engineering education?
You want me to take that? Yep, I'll let you have you jump. I wish I had an easy answer. If we had an easy answer, we wouldn't have a gender gap, would we? I think it's a complex problem, but I think we're tackling it. We're at 35% as opposed to 18%. We're not alone. Mary Flanagan, I was in a meeting, she's a computer science and digital arts faculty member, and she's upset about the low numbers in computer science, which are worse than engineering. And her phrase was she wanted 50-50 by 2020. I think we want to beat her. 50-50 in 2019? I don't know. Doesn't have the same ring, so I don't know if that's going to work. I think Engines 21, getting women in to actually learn how to do things in the machine shop, empowering them, having role models, having impact. Women tend to want to have more of an impact, using a collaborative as opposed to competitive atmosphere. All of which things I think we're trying to tackle. So,
I want to add one thing, because if that's the goal, intro to biotech, the ratio is 60-40. 60 women, 40 male.
Well, I shouldn't say this, but I was at Cal Poly in the architectural engineering department. It was 50-50 15 years ago. So that's our target. Different departments attract women differently, and that's a pretty known fact.
I mean, what's remarkable here is that it's 35% across the board rather than specific disciplines, and I think my view is the interdisciplinary structure, the project-based learning, the things we do with students from the beginning to get them comfortable in the labs and have them focusing on real-world challenges are motivating to a much broader cross-section of students.
The other thing that you can do is you can bring them into the labs and hire them to learn what you're doing and work with you in the lab.
Right.
I don't think we've ever had a time when we have had fewer than 6 women working in our lab, and from time to time it's many more than that. And you bring them in, and very quickly they get real comfortable and they see what's going on. And if you have a whole bunch and have an atmosphere that's welcoming, more folks want to come in and join you.
I think that we need to rethink the whole way that the world thinks about engineering, honestly. You ask anyone on the street who goes into engineering? The majority response is going to be people who like math and physics. It's not going to be, the response won't be people who want to go and fix the problems in the world.
Right.
People who want to have impact become engineers. And most of the women I know who are engineers really don't care about whether they need to learn to drill a hole along the way or solder a circuit or program a computer. They've got a broader objective in mind about having impact on the world, and these other tools and techniques are just things you got to do to get there. Whereas the traditional view of how we've looked at engineering is that it is the tools, and it's not what it's about.
So I think that's.
So we need to rethink. how we talk about it.
Very, very well put. There's a challenge for the National Academy there to help us manage that conversation nationally and broadly. I think that's a very important point. So we have about 8 minutes left. I wanted to take the time to open it up and see if there are questions from the audience. I have a whole list more that I can go through, but so when I call on you, I will ask you to direct a concise question to one or at most two individuals, and I will ask for, please, concise responses. Ross?
I'd say Saul and to John, you've reminded me in your stories that we have such short terms here, and I've always been amazed by what students can actually get accomplished in that period of time. I was wondering if you could sort of tell us a story of the best projects that you've been amazed that can actually get accomplished in a 10-week period of time, from go find a problem to there's a way to know it's going to be patented and marketed, all those sort of things. I don't know if you have one in particular.
Okay, so each of you a very quick example.
So Dartmouth has these 10-week terms where students are taking up usually 3 classes. So the intensity is ratcheted up so high. But that is, I believe, highly conducive to problem solving and design, because some things just don't work well on a slow burn. Sometimes it's got to be all in, all you're thinking about day in, day out, even when you're asleep. And that's what we see in the Thayer students. And so that shows up. I mean, I see it in courses like 146 with the die wheels, and I've seen it in students I've advised in their capstone design engineering 8990 projects, which John will probably comment on.
So is there a specific example you would cite, or too many to count?
I think a good one would be like there was a project, a humanitarian engineering project to redesign a water pump in Haiti, and that one was really challenging because it was also at a distance, and they had to figure out problem solving with all these logistical challenges as well. So I was particularly impressed that team was able to pull it together and deal with distance, design, hydraulics, mechanics all together in 10 weeks. Really impressive.
Thank you, Saul. But John, a quick example?
I think one of them, I mentioned this young girl who had cerebral palsy and the head stick, and I didn't really finish that story. And student group went down, and she beat out with her head stick on a board with the alphabet that she wanted to play chords. And so this group decided they're going to help her. And so while this isn't, one of the big national or international problems, for this girl it turned out to be a really big problem because she wanted to play music and couldn't. And so the first thing they had to do was to figure out what the cerebral palsy had done to her. And so they set up cardboard pieces that were at a slight slope with different size markings on them to see what she could hit with her hand as a target. And it turned out with one hand she was actually pretty accurate and could hit a pretty small spot, and with her other hand she was very inaccurate and had to hit a big spot. But if you put it in front of her, she couldn't do anything at all. She could only hit things out to her side. And so the group decided, we're going to make her a musical instrument. So they went back and forth and thought about all these things, decided electronic organ for this girl. And so they made up some sort of kludgy keys that she could press to figure out exactly what she wanted them to look like and feel like. But it turns out this girl's an artist, and so she wanted things really well done. So they went down to the machine shop, asked if they were set up to do wood. Not really. Went down to the wood shop, bought some cherry, made this cherry cabinet, went to the machine shop, cut all these keys out that were just the right size, got Casio to donate an electronic organ. This is all in 10 weeks. Hooked up this organ internal to this with all the keys. And the day before final presentations, they went down to Prouty Center where this girl was a patient and put her in front of this organ, this beautiful cherry cabinet organ. And she got in there, looked around, figured things out, and started playing Greensleeves. And so these kids are just completely blown away. And so they do their presentation in front of our audience in the review board, and they show a videotape of this, and nobody can say a word, and they're waiting for the applause, and everybody's like this, So it's like 15 seconds later, finally people applaud. But that has had such an impact on those kids that they followed up with this girl, and it turns out she is very bright. She has 140 IQ, and has gotten into writing music and playing it with this organ, and it's on YouTube. And so it's like,
Wow.
so.
Thank you, John. So one or two other quick questions. Bill, you had your hand up?
So the experiential learning you have talked about so nicely here, and it's mostly in the context of engineering. You have to be asleep to not recognize that there's a movement within Dartmouth to expand experiential learning. And I'm wondering if any of you could comment on lessons learned that might be applicable to our colleagues in humanities, social sciences.
I've been lucky enough to have some pretty good interactions with people in all kinds of different areas, teaching them problem solving, how to set the specifications up so that you really understand what has to be fulfilled for a solution to work, teaching brainstorming techniques, how do you actually come up with lots of ideas, and then weighing techniques, how do you weigh these ideas against your specs, and then what do you do afterwards. And so it works just as well for buying cars, picking majors, deciding what foreign study trip to go on, et cetera. So the open-ended problem solving is really neat because it does work with any department, any division, any kind of problem, and it's something that students take out of 21 and use for the rest of their lives. I mean, I don't know if I should say it, but I'm so thankful for this sort of whole experience that we're having over the last few weeks, because one of the things I found in my email is tons of letters from students who say, here's how I use those techniques. I'm in business, or I'm in education, or I'm in the arts, but I'm using your techniques to do things. So
That's great, John.
I think it
Thank
works
you.
for everything.
So is there one final, very brief question? I said very brief, and the two faculty who had their hands up just put them down. All right, Lee, be brave, be bold, be brief.
I'll give it a shot. I'm asking Tillman and Saul a question. Okay? So, when I teach ES22, I tell the students, school rewards you for answering little questions fast. Life rewards you for asking big questions well. And so, my question to you is, I think we do very good and at times truly excellent work at the level of innovation that can lead to prototypes. Physical prototypes. But an awful lot of big questions we would like students to get their arms around, perhaps, aren't in that category. So do we abandon that and simply say that what we're trying to do is to give them a stepping stone in that direction with prototype projects? Or can we do more to engage people in thinking about the same creative design problem-solving process, but in things where a prototype is just not possible?
I'll start.
You each have 20 seconds to respond, and I'm not kidding.
It's a great question, Lee. And I think that students who are engaged in participating in research in the labs begin to go down that road. And I see it in students who are working in my lab right now, where they're working on problems that will be lifelong pursuits potentially. And they're just trying to get started at this point, understand what's the nature of the challenges, what's the nature of the tools available now, where are the opportunities for innovation, where are the opportunities to move forward, and setting these students up in a way that they can begin that long process is, I think, also part of our mission.
Tillman, you have the last word.
How many seconds do you have?
11.
11. I think it goes back to what I said earlier. At the end of the day, we're contextualizers. And so I think the way you described these problems, our job is to break down big problems into little problems that within the confines of a 10-week class or a 4 or 5 year education, they can see how chipping away at these little problems can make a difference at that scale. And then from then I think they can extrapolate that, guess what? The more we do that, the more you sort of start chipping away at the bigger problems. And I just think we're simply constrained by the time we have them. And many of the problems you're thinking about are not even decades. They could be multiple decades that it will take to solve those. So.
Well, thank you, Tillman. I'd like to thank all of our panelists for interesting responses and stimulating discussion. faculty who are scholars but also educators, clearly dedicated to the learning of our students, and that's one of the things that for me makes it such a wonderful place to be. So thank you all. You can all take your seats, and I will turn the podium over to Dan Mote and the team from the National Academy of Engineering.
Well, Bernie, you like your picture up there? It's good, huh? It's good. Well, I'd offer my welcome. I really welcome the laureates, family, friends, colleagues, and guests. My name is Dan Mote. I'm the president of the U.S. National Academy of Engineering, and it's really my esteemed honor to be here today in this afternoon's program as one of NAE's, indeed the nation's, the most prestigious award in engineering education, the Bernard M. Gordon Prize for Innovation and Engineering Technology Education. As a matter of fact, this is the largest engineering education award in the world, as a matter of fact, not just the United States. We are very excited to have Bernard M. Gordon here and his wife Sophia in the audience today, sitting right here in front of me. Thank you all very much for that. Bernie has earned more than that even. He's a great supporter. Also with us today is Mr. Nicholas Donofrio, a committee member and one of the Gordon Prize Committee advisors. Oh, is not here today, but Nick is here. Nick is here. Thank you very much, Nick. And now let's take the opportunity to learn a little more about this remarkable engineer behind the Gordon Prize.
The Bernard M. Gordon Prize for Innovation in Engineering and Technology Education was inaugurated in 2002 by the National Academy of Engineering. The intent of the Gordon Prize is to recognize new modalities and experiments in education that develop effective engineering leaders. Now, for over 10 years, the Gordon Prize has recognized individuals that have innovated in areas such as curricular design, teaching methods, and technology-enabled learning that strengthen students' capabilities and desire to grow into leadership roles.
The award was created to recognize professors, teachers in technical institutions who understood that there was much more to engineering than learning theory, and that there was a need to inculcate, not in everyone, because that's not possible, an attitude. There's an old phrase that it takes knowledge, skills, and attitude to be a successful engineer, let alone an engineering leader.
This knowledge, skills, and attitude propelled Bernard M. Gordon to found or contribute to multiple companies and institutions throughout his long career. earning over 200 patents, being awarded the National Medal of Technology, being inducted to the National Academy of Engineering, among numerous other honors and awards. In general, embodying the very spirit of his namesake award.
So this attitude is one, you don't get born with it. It's one that gets developed by your teachers, the successes of your jobs, your understanding that after a while you're expected to do that. And it's a hard thing to put into words.
Fostering these leadership skills in engineering is vital to making the profession personally rewarding, successful in the competitive marketplace, and enriching to society at large. The Gordon Prize recognizes educational efforts that cultivate this leadership.
Both the National Academy of Engineering and I together recognized that the educational process in technology had changed so much over the past decades that there was now a dearth of engineering leaders. It does not take a large percentage of engineers to be leaders. It's about the same ratio as a platoon leader to a combat platoon. 1 in 20, if you can get 1 in 20 engineers to have the capability, the desire, the will to be the leader, you increase the productivity tremendously. It's not about academic achievement, it's about industrial, real world, turning out products that society needs that will enhance the economy of the United States.
These leadership qualities are critical to America's competitiveness in the 21st century. The teachers and educational approaches that are recognized by the Gordon Prize are an immense service to the engineering community, to the engineer as an individual, and make the world a better place for all.
Now, ladies and gentlemen, I'd like you to please welcome to the podium with me Mr. Bernard M. Gordon. He's the chairman of BMG Charitable Trust. And is Dr. Philip Hanlon here? Oh, great. Thank goodness. I hadn't met you yet. And also Dr. Hanlon, president of Dartmouth College. Both will assist me in the presentation of the awards. Now, our presentations awards will probably take place right about here, I think. Okay. We have it ourselves. Can we line people up here roughly?
Yeah, and Brian, you can come right here.
Okay, great. Excellent. Okay. Well, the recipients of the Gordon Prize receive a $500,000 cash award, half granted to the recipients and half granted to the institution to support the continued development and refinement and dissemination of the recognized innovation. In addition, the recipients receive a medallion and, of course, a very fine certificate for their historical record. The recipients are really invited to present also a public lecture on their innovation during the National Academy of Engineering's annual meeting on Sunday, September the 28th, 2014. The 2014 Bernard M. Gordon Prize for Innovation and Engineering Technology Education recipients this year are Dr. John P. Collier, Dr. Robert J. Graves, Dr. Joseph G. Helble, and Dr. Charles E. Hutchinson. Their citation reads, "For creating an integrated program in engineering For creating an integrated program in engineering innovation from undergraduate through doctorate to prepare students for engineering leadership." I will now call each of the recipients to the stage to receive their prize individually and have their picture taken to memorialize this occasion. After all four has received their prize, we will gather together as a group for a group photograph up here together. So I'd like to start by asking Dr. John P. Collier to come forward. Dr. Robert J. Graves. Dr. Graves. Congratulations. Okay, right there. Right there. Well done. Dr. Joseph J. Helble. And Dr. Charles E. Hutchinson. Come right in here. Okay. Where are you? Right here?
Are you okay right here? You think you can come back for them?
See, do you want the...
Push the board when it's here, and you want it in. We have to make do with this space here.
Oh, that's right.
All right, yeah, I think this will work.
Well, you don't want this podium in the way of this.
You're right there, can you get?
You sure? All right. Okay.
So on behalf of my colleagues who have joined me here on the stage, I'm deeply honored to accept this award for Dartmouth College and for the Thayer School of Engineering. Our sincere appreciation as a community goes to NAE President Dr. Dan Moat, NAE Executive Director Dr. Lance Davis, Ms. Deborah Young from NAE, of course Mr. and Mrs. Bernard Gordon for making this award possible, and members of the Gordon Prize Selection Committee represented today by Nicholas D'Onofrio, who I know is here or was here somewhere in the back. Thank you, Nick. And I thank you all for traveling to Hanover to present and celebrate the Bernard M. Gordon Prize. The award was established in 2002, as we heard a few minutes ago in the video, and it's being presented at the recipient institution for the very first time. So we are privileged to have this opportunity to host you for this ceremony. In recognition of the significance of this award to Dartmouth and the Thayer School of Engineering, we're also honored to be joined by Dartmouth President Philip Hanlon here on the stage. Several members of the Thayer School Board of Overseers, please raise your hands so we can see who you are. Thank you. And members of the Engineering Management Corporate Collaborative Council, please raise your hands. So thank you to our board representatives for joining us here today. And of course, we're joined by our families and friends, faculty and staff, colleagues, our students, and by the greater Dartmouth engineering alumni community, many of whom are joining us again by live streaming of this event. In particular, I'd like to thank our students and alumni. The Thayer School of Engineering would not be what it is, and we would not be here today without your boundless energy, limitless intellectual curiosity, and your willingness to tackle whatever the faculty throw at you, as true today as it was 50 years ago when our school and our curriculum began the early steps to take its current form. Now, about 5 years ago, I took a look at engineering course catalogs from several major research universities, both public and private, comparing their engineering programs from the present, from the 1980s when I was a student, and from the 1950s. And what I found is that little had changed. There was virtually no interaction between engineering departments at the undergraduate educational or curricular level, no opportunity for, say, a mechanical engineering and electrical engineering student to work together in the same elective course or work together on integrated project teams. True collaboration with business schools to help teach skills associated with technology entrepreneurship were limited, and PhD programs remained structured the way they had been for nearly a century. The departmental silos for which academic institutions are frequently criticized were very real. The Bernard M. Gordon Prize has, over the past 13 years, recognized those institutions and those programs that have taken significant steps to break this mold, to engage students to cross disciplinary boundaries, to take steps to prepare them to become engineering leaders. At Dartmouth, here at an institution where our faculty have long been as dedicated to our teaching as to our original scholarship, we are deeply honored to be recognized in the company of these prior recipients. This award celebrates our problem-based focus in undergraduate engineering education, beginning with the required first course in engineering problem solving, Engines 21, that you heard about in our panel discussion, whose simple title, Introduction to Engineering, seems to say little, but if you think about it, at the same time, this is an introduction to engineering. It speaks volumes about the creativity, innovation, and entrepreneurial opportunity that represent the best of what engineering can be. It celebrates our strong partnership with our business colleagues and our Masters of Engineering Management program, where students gain understanding of the business elements of assessing and developing technology. And it recognizes our more recent experiment in PhD education, the creation of our PhD Innovation Program in 2008, a program that challenges some of our PhD students not to rely on others, but to apply their own scholarship directly, to put their work to immediate use to benefit the greater good by becoming PhD-level technology entrepreneurs. Combined, these programs are the pillars of the Dartmouth Engineering Entrepreneurship Program, a comprehensive effort to teach engineering students that they have an opportunity through their work to have an immediate and measurable impact. And they provide us the opportunity to teach our students and remind ourselves that as engineers, we have made a commitment to use science, and here at Dartmouth, our liberal arts education, to understand the world and then to use engineering to change it. On behalf of my co-recipients, John Collier, Charles Hutchinson, Robert Graves, and of all who contribute to these efforts, I thank you, thank the National Academy, and thank the Gordons for this award. We are deeply honored. Thank you.
thank you, Joe, very much for your very thoughtful and perceptive remarks. I very much appreciated your distinction you made between engineering and engineer. It's a very important distinction, not often thought about. But over 25% of the members of the National Academy of Engineering have no degrees in engineering. In fact, many have no degrees at all, as a matter of fact. They have been elected to the Academy because of what they have done, not by what they have studied. And so that distinction is very important, and it's very relevant to the discussion you had today. It's now my great pleasure to really ask to the podium the president of this famed institution, President Hanlon, to consider his remarks to the laureates on this very special day. President Hanlon.
Thank you, Dan, for joining us here today, and also to the Gordons for making this prize possible. And of course, I want to congratulate John and Robert and Joe and Charles for this amazing recognition of your and your colleagues' work here. When I travel around and talk to alumni, a pretty standard thing is that they will express their regrets that they didn't take this kind of course or that kind of course when they were during their time at Dartmouth. And I'm an alum, so I can come clean with my regrets. And my regret is not taking Engine 21. I'll need the non-recording option, I think. So my best friend, Dave Voss, was in Engine 21, and I can still remember the problem that they were faced with that year and what his group came up with. But what I remember even more is thinking, you know, how cool is this, that they're actually looking at some sort of problem where the answer isn't known. Me being a math guy, you know, I was well aware that the answers to all my math problems were known by somebody. And here they were out sort of in uncharted territory, and I thought, this is just the coolest thing in the world. So to this day, I regret that I never got into Engine 21 or never decided to pursue it. That's only to say that this is a tremendous day, a tremendous recognition for the Thayer School, for your faculty, students, and alumni, and an important day for Dartmouth, one that the whole campus is proud of. Today represents more than just an important professional recognition of the innovative work going on in one of America's very best engineering schools. Today really highlights the hard work being done day in and day out by Dartmouth faculty who are truly committed to innovative education of our students, helping create Dartmouth grads who are known the world over for their ability to take on some of the most pressing problems in the world. So the Thayer School has always been an essential piece of this vision for Dartmouth. Exposure to engineering sciences has never been more relevant or more complementary to the modern liberal arts education. And it's never been more in demand by our students. This year we have more than 100 engineering majors in our senior class. That's an all-time record for Dartmouth. And the demand amongst all students for engineering courses is also at a record high. So the visionary faculty members who we're celebrating today are recognized for the importance that they've placed on entrepreneurial thinking and action-based learning through the great Engines 21 course that I mentioned before, the Master of Engineering Management program, working with our Tuck School, and the PhD in Innovation. So the work of the Thayer faculty, they not only tap into the really natural innovative mindset of our students, the desire of our students to make a difference in the world, to change the world, but it also shows how they're looking for ways to teach students to put theory into practice and really get ready to forge new knowledge when they enter the world. And this is going to be key to all areas of Dartmouth, not just the Thayer School, as we transform our undergraduate education to stay at the forefront in a world that's really changing rapidly around us. So I applaud what the faculty being recognized here today have done. I thank the National Academy of Engineering. This is a really meaningful and very special day for Dartmouth, so thank you.
Phil, Dan, Bernie, and everyone who's gathered here, I thank you again for your kind remarks and for this distinct and distinctive honor for the school. With that, we conclude our formal presentation, and I ask that you all join us for a reception immediately afterwards to celebrate this afternoon in the atrium, right out these doors and right down the hallway. So thank you very much for coming, and I hope to see you outside in a few minutes.